before we start with 2.1. And it's good that you guys want help now, because if you wait too long and the test rolls by.
65.
Which section?
1.3.
1.3, 65. 1.3, 65. Something about a cosine of beta. Cosine of beta is equal to 0. Sine of beta is equal to 1. It's saying, without a calculator or referring to a table, find the value of beta using the given information. We did this in class, remember? This is the x value, and this is the y value. So at what points? At what points is the x 0 and the y 1? At what angle is x 0 and y 1?
45.
This is 45. 90? You guys think it's 90?
Yeah.
Yes, you're right. Because at 90, the x is 0, the y is 1. So that implies beta has to be 90 degrees. And recall, we actually calculated the sine, cosine, tangent, secant, cosecant for this specific case when we did the quadrantal angles. You guys remember that? That was last class, I think. No? 2 classes ago? I don't sleep much. All the days are kind of mixed. Yeah, you get it, huh? Yep. Does that make sense?
Yes.
Okay. So what if cosine of beta equals -1, sine of beta equals 0? What is beta now? 180? Yeah, it's 180. Just because I ask it with an inflection in my voice that implies skepticism doesn't mean you're wrong.
I was thinking serious. I was thinking 180.
You say 180, I'm like 180, and you're like, well, actually, maybe no. I love when that happens. I get a kick out of it because A, it's funny. B, it tests your knowledge. What I want is for you to be like, no, it's 180. I'm 100% sure. That's the only position in which cosine has -1 and sine has 0. Here's how you remember it. Cosine parametrizes x values. Sine parametrizes y values. Why is this the case? Because on a unit circle, every radius, which is your hypotenuse, has value 1, right? And this is your x and your y. And this is your theta. So, or let's say your beta. So your cosine of beta is going to be adjacent, which is x, over hypotenuse. Well, hypotenuse is 1. Anything divided by 1 is what? Just itself. That's why cosine parametrizes the x on the unit circle. And sine parametrizes the y on a unit circle, because sine of beta is equal to opposite over hypotenuse. But what is your hypotenuse? 1, because you're on a unit circle, a circle of radius 1. So this ends up becoming y. This is why we say sine parametrizes the y values on the unit circle. So whenever you think sine, think y value. When you think cosine, think x value. Easy as that. Okay, got to move on. But if I get through this section, we have a little extra time, feel free to ask questions. Also, feel free to come in here before class starts and ask questions. Also, feel free to stay after class and ask questions. Also, feel free to go to tutoring and ask questions. Moving on to 2.1. Chapter 2 has 4 sections. At the end of those 4 sections, you'll have your first exam over chapters 1 and 2. A right triangle view of trigonometry. Okay, so let's talk about right triangles. So let's say we got a right triangle. Let's call this alpha, call this beta, call this x, call this y, call this h for hypotenuse. Okay. What is the sine of alpha? Yes. What is the sine of beta? Huh? What's sine of beta? Why are you guys acting like there's stuff to write? When we're done writing, I've been standing here. What's sine of beta? X over h? Oh, why? Opposite of this angle, right? So when we say opposite, we mean when we have this angle, what's the leg opposite to the angle? It's x. Over here, when we had alpha, the leg opposite to alpha was y. That's why sine of alpha is y over h versus sine of beta is x over h. So what's cosine of alpha? Say it out loud. Cosine is what? So what is the adjacent leg to the angle alpha? Yes. So it's x over what? Very good. More on this later. What's the cosine of beta? Y over h. More on this later. Y'all notice something there? What do you notice? Yeah. What's going on there? What's going on there? More on that in a little bit. What about tangent of alpha? What's this equal to? Y over x. What's tangent of beta? Okay. So now you get that. So let's say we have a triangle. So 30, 60, 90, right triangle. Let's say this is root 3. This is 1 and this is 2. Okay. What is the cosine of 30? Square root of 3 over 2? Why? That's that. That's that. And that's that. Right? What's the sine of 30? One over 2. What's the tangent of 60? Ah. Guys, do you see what's going on here? You'll be expected to know how to do this. Okay. What's the cosecant of 60? One over sine of 60, right? So that's 1 over what? What's sine of 60? Square root of 3 over 2. And then when you multiply by reciprocals, where's my calculations here? Oh, it's right here. 2 over square root of 3. And then when you rationalize the denominator, you get 2 root 3 all over 3 is equal to your cosecant of 60. Make sense? So, this is disgusting. This is disgusting. I don't like how this book presents this stuff. At least this part. Oh, well, actually, it's not that bad. Let's do it in the second section. Yeah. I don't like the logical flow of this. But let's create a table of sine and cosine values for special triangles. So one of our special right triangles is our 45, 45, 90. And the other one is our 30, 60, 90. Okay. Yeah, of course. So if this is 1 and this is 1, what is the hypotenuse going to be? Yes, so it becomes what? Square root of 2. Square root of 1 squared plus 1 squared is equal to square root of 2. Because 1 squared is 1 and 1 plus 1 is 2. And when you put the square root, it retains that. So because we can scale triangles by the same arbitrary value, if you scale all of them together, we can replace a 1 with the x, a 1 with the x, and this with the root 2x. Remember? So same thing for here with the proof I had earlier. If this is your root 3, this is your 2, then this is your 1, x. Remember I showed that? I showed it before when we talked about special triangles, that you can scale these triangles by some arbitrary factor x. I utilize it in the proof to show that in a 30, 60, 90 triangle, that these values are held utilizing the Pythagorean theorem. Okay, so what we want to do is we aspire to find that given a theta, what are all the sine, cosine, tangent, secant, cosecant values? But most importantly is sine and cosine, okay? So let's do that. Let's create a table. So here's your theta. Let's have 30 degrees, 60 degrees, 90 degrees. Oh, and actually, let's throw in a 45, 30, 45, 60. Actually, 30, 45, 60. 90 is trivial. We won't consider 90 for now. That's trivial. And we want to know what is sine of theta and what is cosine of theta. So when I construct a table like this, sine of theta, if this is theta, means this is sine of 30 degrees. So what is the sine of 30 degrees? Say what?
X over 2x.
Yes, opposite over hypotenuse. Notice that the two x's cancel out and you get this, right? The 2x is not the 2x. So this ends up becoming a 1/2. What is sine of 45? Should have put a 30 here. What's the sine of 45? X over square root of 2x. X's cancel. So what do you get? You get a 1 over what? And when you rationalize the denominator, you get root 2 over 2. So over here, we're going to have a root 2 over 2. So what is the sine of 60? Square root of 3x over 2x. X's cancel. So this is just root 3 over 2. What's this x business? Again, this shows you that you can pick any x. Pick a number. 4. We could create a 30, 60, 90 triangle that has hypotenuse 4 times 2, which is 8. This kind of like 4. And this kind of leg 4 root 3. That's what that x means. Pick another x. 6. That means we could create a 6 root 2, 6, 45, 45, 90 triangle. Whatever you want x to be, you can create a triangle that scales that way. That's why that x is there. That's why we keep canceling it, because everything scales uniformly. So something like that can be canceled. So over here, sine of 60, we get root 3 over 2. What about cosine of 30? Square root of 3x over 2x. Because it's adjacent, or hypotenuse. And then the x's cancel. So then we get root 3 over 2. So we're going to put that right here. What's the cosine of 45? Eh? What'd you say?
X over the square root of x.
X over square root of 2x. So this becomes 1 over square root of 2. When you rationalize the denominator, you get root 2 over 2. So this becomes root 2 over 2. And what is the cosine of 60?
X over 2x.
So you get a 1/2. Now let's include that 90 degrees. What is the sine of 90 degrees? What is the sine of 90 degrees?
Isn't it square root of 2x? No.
What is the opposite of 90 degrees? What is the hypotenuse of this triangle? That's another way to think about it. Anything divided by itself is 1. What about the cosine of 90 degrees?
Square root of 3x over 2x.
That's where this analogy breaks down. Right? Cosine of 90 degrees is 0. Why is that? This analogy is actually not appropriate because it doesn't work in all cases. So remember, we use triangles to study the circle. All right. I'm gonna go away from what the book is showing. I want to show the unit circle right now, because the book is not showing the unit circle right now, but I want to show it right now. So guess what? I call the shots. I call the shots. So I'm going to show you guys a unit circle. What does it mean to be a unit circle? it means that the radius is equal to what? 1. A unit circle is a circle of radius 1. So that's why over here, this is at 1, 0. So what is it over here? Yeah, 0, 1. This is 90 degrees. So cosine of 90 degrees is 0. Sine of 90 degrees is 1. That's why that's happening right there. So cosine of 0 degrees would be what? Yeah, and sine of 0 degrees would be what? Yeah. What is it over here? -1, 0. So what is the cosine of 180 degrees? Huh? -1. Why? Why did you pick -1? Why didn't you pick 0? Cosine parameterizes x. Remember that. That's very important. Cosine parameterizes x. When I say cosine, you say x. Sine parameterizes y. When I say sine, you say, there you go. Cosine, sine, there you go. So over here, what are the sine and cosine values? Aha! You're really getting it now. So let's fill in the unit circle. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. We're going to fill the unit circle for all of these values. Really, that's neat. 3. Okay, so let's say we move 30 degrees here. Let's say that this is 30 degrees right here, all right? And you want to know what? Let's use the color yellow. All right, let's say that's 30 degrees. What are the sine and cosine values? Because notice that from right here, we can create a right triangle. That becomes a 30, 60, 90 triangle, right? Here's your x and here's your y. What are the sine and cosine values here?
Sine of 1 cosine is square root over 2. Square root of 3 over 2.
How did you know that, young man?
And we just did it on the chart.
Well, because we just did it on the board. It's right here. It's a consequence of a 30, 60, 90 triangle. Where x is what? We said x equal to what? Huh?
Any number.
Any number, but in this very case, what number is it? 1. Very good. Oh, well, actually, technically, in this very case, x is equal to 1/2. Because, why does I say 1/2? Because this hypotenuse is the radius of the circle. We're dealing with a circle of radius 1. What do I have to multiply 2 to make this overall thing a 1? A 1/2. So x is 1/2 technically. But that's not the same x as this x. This x is root 3 over 2. And this y is 1/2. Okay? All right. Now let's move on to 60 degrees. can make another right triangle. A 30, 60, 90 triangle. What are the associated sine and cosine values here? What? Won't they just flip? Yeah. What flips? Me? Oh, the x and the y? Yeah, you have to take differential geometry to see me do a backflip. I'll box jump this table and do a backflip. It's really not that hard. If you practice on a trampoline, the backflip is pretty easy once you're at that height. Just tuck your legs in. Now, what if this angle? Oh man, what am I doing? Oh, what am I doing? Yes, you figured it out. But this young lady was totally correct in flipping it, but we just did it too early. I do not mean to besmirch. I do not mean to besmirch your insightful idea. You're right, but what we had to have written is up there. So don't think you're wrong. It's just I jumped the gun, okay? So they flip. So here's 1/2, and here's √3/2. Okay, and this is 60 degrees. But let's discuss 45 degrees. What is cosine for 45? Yes. What is sine for 45? Same thing. Interesting. Okay, so look, we filled out the first piece of the unit circle, the first quadrant of the unit circle. What is this thing talking about? Well, it's saying at these angles, we can always create a right triangle. Right? Move an angle, you can create a right triangle. Move an angle, you can create a right triangle. And the sine and the cosine values are different at each angles. Notice here, when you move 30 degrees, you get a 30, 60, 90 triangle, which has these values in the yellow. You move more than 30 degrees, you move 45 degrees, and you get these orange values, √2/2. Then you move even more, you get 60 degrees, and you get this 1/2 √3/2. And then you move even more to 90 degrees, and you get 0 and 1. So what degrees is this going to be? And what degrees is this going to be? And what degrees is this going to be? We know this is 180. And we know this is 270. And we know this is 0 or 360. What's this one? What's the next one? What's the angle?
They put it from the 90 to the next one, or do you have a 180?
No, yes, from go beyond 90. Who here's seen this before? The unit circle? Kind of?
I've seen people like studying.
Okay. Have you guys ever taken this kind of stuff in high school? Oh, okay. Good. Most people in high school just memorize it. I'm going to teach you how to derive it with no memorization needed, okay? So here's how you come up with the special angles. The special angle of 0, 30, 45, 60, 90. What's going on there? 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees. What's going on here? What's going on here is a pattern. It's called a 30, 15. The 30, 15, 15, 30. That's why it's kind of confusing. So 30, 15, 15, 30. Remember that. 30, 15, 15, 30. That's the only thing you really have to memorize. 30, 15, 15, 30. Can you memorize that? Okay, it's pretty easy. That's what's happening. You start off at 0, and you add to 0 30, which gives you 30. Then to 30, you add 15, which gives you 45. Then to 45, you add 15, which gives you 60. Then to 60, you add 30, which gives you 90. This 30, 15, 15, 30 pattern repeats. So if 30, 15, 15, 30 repeats, and this is at 90 degrees, what degrees is this? Yes. Very good. Now, what are the associated sine and cosine values? Because we can form a right triangle here. No guesses?
Over the y-axis, so that means this is over the
Which parts? The x or the y parts? Yes. So the x part is going to have a negative on it. But what is its numerical value?
it's just a negative 1.5 now.
Precisely. Now, what is the y?
Starting at 3 and 2.
Yes. Because this y length and this y length are the same. And this x length and this x length are the same. Hence why I did it all in the same color. I'm jumping to great lengths here, guys. I don't gotta color code this stuff. This color chart costs like 25, 30 bucks. I hope it helps. Time for orange. What are the associated sine and cosine values? And before that, tell me, what is the angle here? 135. He's like, oh, wait, no, it can't be right. I'm going to put it in the calculator. No, you're right. You see how I find it hilarious? Very good. 135. So what are the associated sine and cosine values?
Negative 32.
That's correct.
Positive.
Yes. Why is it positive? X is negative, but why is y positive? Yes, because it's above the x-axis. All y values above the x-axis are positive. and all y values below the x-axis are negative. All y values to the right of the vertical, all x values are positive here, and on the vertical, all x values are negative here. So that's why this negative is happening. Very good. Next one. At what angle is this one at?
150.
150? What?
Yes, it's 150.
Why is it 150?
You have 15.
30, 15, 15, 30 says that's got to be 150. Okay. So what are the associated sine and cosine values? I should say what are the associated cosine and sine values? Because cosine is on the left. And in English, you write from left to right. What did you say?
Negative square root of 3 over 2.
And
Positive 1/2.
nice. Oh, this one's solved already. So move on to the next one. We are now entering the what quadrant?
Third.
Third quadrant. So what is the angle here? Huh? So 180 is right here. What is the angle here?
210.
210?
Yes, 210.
Aha, I like the confidence. He's like, yes, 210. What are the associated cosine and sine values?
One is negative x and positive 1, right?
No, they're both negative.
Oh, they're both negative.
Negative half. Negative square root of 3 over 2.
So which ones are which? Give me cosine first. What is cosine?
Negative square root of 3 over 2.
Why do you say that, young lady?
Because the x didn't change.
Because the what?
Because the x didn't change. Because cosine means x, right?
Yes.
So it's still where x is negative.
Yes. But why did you elect to say this numerical value? Why not negative 1/2? Why not negative root 2 over 2? Because if cosine is the x, notice that the x here is of the same length as the x in the second quadrant as it is in the third quadrant. That's precisely why. Hence why I utilized the yellow chalk. So what is the y parameter? Huh? Negative 1/2.
Yeah.
Ah, I like the confidence. Why do you pick negative 1/2, young man?
This, sine is associated with y, right?
Say what?
Sine is associated with y.
Yes, but why did you elect the numerical value 1/2?
It was something we used it on 150, so negative. It's positive up there, it's negative.
Yeah, I want you guys to see these patterns. I want you guys to see these associated patterns of from here to here versus from here travel across. Yeah, see those patterns there. Once you see those patterns, it'll be easy to just derive the unit circle on your own. You don't have to memorize this stuff. I don't want you to memorize the unit circle. I want you to be able to derive it using 30, 15, 15, 30, and just this table. So on to the next one. At what angle is the next one at? Say what? 225? Yeah, when I do it too much, it loses its power. So What are the associated cosine and sine values?
Negative, square root of 2 over 2. And then negative, square root of 2 over 3.
Why do you say that?
Because the y is underneath the x-axis, so that means that it's negative.
Okay, you got the reason why it's negative because it's in the third quadrant. But why did you elect to pick these numerical values? Root 2 over 2.
They're on the other side. On top, across.
Yeah,
It's just negative because it's one.
yeah. Reflected. But also over here. These root 2 over 2's always pop up at the 45-degree analogs in each quadrant. So they're going to pop up at the 45-degree analog in this quadrant. You'll see. But all that changes is the sign, right? The sign tells you which quadrant. The numerical values tell you what angle. Okay, what's the next angle? 240. And what are the associated sine and cosine values at 240?
Negative 1
And
negative square root of 3 over 2.
where are you coming up with these values?
Because it's reflected in the location of where the
Isn't that cool? Isn't math cool? It's like art, huh? It is. Mathematics is an art. It's just not just pictures and diagrams, but we also invoke critical thinking and logical deductions. This is really why they make you guys do this, because learning how to think critically helps in any aspect of life. Whether you want to bake a cake or perform a tracheostomy, it's going to help you in any of those cases. Moving on, what's the next angle? 270, we already figured those values out. What's the next angle here? How do you know that?
30, 15, 16, 30.
I see. Okay. So what are the associated sine and cosine values? I mean cosine and sine. What am I doing? Oh man, I'll mess everything up. It's that sound. It's that sound's fault. I have ninja training, so when I hear stuff, I'm ready to go. So when people make sounds, I'm wondering if it's time to go or not. Clearly it's not. Ha! Okay, there's nobody back there. I had to check. What are the associated sine and cosine values?
I think positive 1 half and square root of 3 over 2. Negative.
Why? In fourth quadrant and across. Okay. Okay. What's the next one?
Negative square root of 2/2.
What's the angle? 315. What's this associated cosine and sine values? Square root of 2/2. And what? Negative square root of 2/2. Why? Okay. Last but not least, what is this angle?
I need some colors.
330.
330. And what are the associated sine and cosine values?
Square root of 3/2.
Beautiful. We have completed the entire unit circle. Remember when I said trigonometry is the study of utilizing triangles to understand a circle. Do you see what I'm saying now? We're using triangles to parameterize how does a circle change. We're measuring how does the value of the circle change based off of the x and the y legs. We're measuring how a circle changes. Okay?
Can I take a picture of that? Yeah.
No. The picture should be in your brain. You should be able to derive this on your own.
I need time to drive it.
Yeah, well, no pictures. Maybe after class,
Okay.
but that's if that thing is up on the board. Yeah, no technology, man. I don't play around. I don't play around. I've had teachers do that to me too. I wanted to take a picture of something and they said no. And it was for my own good. Back then I was like, oh man, come on, just let me take a picture. But really it's actually for your own good. You should be able to derive this for yourself. But you know, there's the video, recorded video. You can look at the whole recorded video on the internet. It's on YouTube and it's on Canvas. So there's no reason to pull out your phones out and start snapping pictures, even for that. So twofold reasons why not to do it. Okay. So this is what we call the unit circle. And all these x and y values are the sine and cosine values for all of these angles. This is a very, very important concept in this class. You need to know how to derive this whole thing on your own. Start off with just a circle and a coordinate system. Place the different angles using 30, 15, 15, 30. And then place the associated sine and cosine values. This will need to be something that you know very, very well. It is going to come up over and over and over and over again in this class. So get very familiar with it very quickly. Okay, now that we talked about that, let's talk about cofunctions. What is the sine of 30 degrees? Is that how I should be doing it? No, that's not how I'm going to do it. I'm gonna call this beta. I'm gonna call this alpha. What's the sine of beta? Y over H. Okay. What is the sine of alpha? What is the cosine of beta? What is the sine of alpha? Sine of beta, opposite over hypotenuse. Sine of, cosine of beta, adjacent over hypotenuse, that's right. Sine of alpha is opposite x over. Something seems off here. Sine of beta is opposite over h. Sine of alpha is opposite over h. Cosine of beta is opposite, or cosine of beta is adjacent over h. And then sine of alpha is opposite of, what's going on here? Huh. What's going on here?
Sine of alpha twice.
That's why it's sine of alpha. I mean cosine of alpha. What's the cosine of alpha? Y over x. Cosine of alpha. Yeah. Okay. What do you guys notice? Not necessarily, but it's only when that happens and this happens. Right? What's going on there?
Isn't there a 45, 90 triangle?
That's why I deleted the angles. Yeah. So notice in this triangle, alpha plus beta plus 90 degrees equals 180 degrees because we are in flat Minkowski space-time. Euclidean geometry, no curved space, just flat. What if I subtract the 90 from both sides? Isn't that right?
Yes, sir.
What if I then solve for, let's say, alpha? So that means sine of alpha is equal to x over h, right? But that's equal to sine of 90 degrees minus beta. So in short, sine of alpha is equal to sine of 90 degrees minus beta. You can see that? Whoa, wait. What am I saying here? Yeah. Okay. That's right. Sine of alpha is equal to that. But notice, sine of alpha also equals what? Cosine of beta. Right? Orange. Right? So that means this equals sine of 90 degrees minus beta. That means cosine of beta is equal to sine of 90 degrees minus a beta. This is called a cofunction property. That's precisely why they're called sine and cosine. Because cosine is the cofunction to sine. And let's derive the other cofunction identity. So we have cosine of alpha is equal to y over x, which is equal to sine of beta. But remember, we did some mathematics where we said alpha plus beta plus 90 degrees is equal to 180, which then we solved for alpha and we got alpha is equal to 90 degrees minus beta. So then this is the same thing as sine of, oh, this is the same thing as cosine. Huh? Cosine of alpha is the same thing as cosine of 90 degrees minus beta, because alpha is the same thing as 90 degrees minus beta. And so we get our other cofunction identity. Here's the other cofunction identity. It's because sine has cofunction cosine, and cosine has cofunction sine. It's all just a consequence of changing your frame of reference of angle. So let's do a problem with regards to this idea. Let's say we know that the cotangent of 75 degrees is 2 minus root 3. Find the exact value of tangent squared 15. So here's our given information. Here's what we want to show. We want to discover what is tangent squared of 15 degrees. Okay. So we think about what is cotangent of 75 degrees anyways. Cotangent of 75 degrees is the same thing as sine of 75 degrees, or I mean cosine. Cosine of 75 degrees over sine of 75 degrees. We know it equals 2 minus the square root of 3. But we want to find tangent squared of 15. Okay? Somehow we have to convert the given information into a tangent. And then somehow we have to change the 75 to a 15. How are we going to do that? This is another cofunction identity. That's why it's tangent and cotangent. That's why they're called that. So, can we use that cofunction identity? Notice that this is another cofunction identity. Maybe this will make it easier. That one makes this problem very obvious. Let's use that one. Cotangent of, let's set beta equal to 75. So 75 is playing the role of beta. So cotangent of 75, something whose numerical value we know explicitly, is equal to tangent of 90 degrees minus beta. But beta is 75, so we get this. Is that not true? Is that not true? It's true, huh? Okay. So this is how we get that tangent 15 to appear. But look, tangent 15, when we go all the way back, is equal to cotangent 75. But cotangent 75 is equal to this. So this thing is equal to 2 minus square root of 3. And we aspire to find what is tangent squared 15. So why don't we just square both sides of the equation? Square this, square this. Then I get tangent squared of 15 degrees is equal to this quantity squared. And you're done. You were given the cotangent of 75 degrees is equal to 2 minus square root of 3. You were asked to find tangent squared of 15 degrees. This problem was begging you to utilize a cofunction identity. Okay, now that you know why cofunctions are called cofunctions, create a cofunction identity for secant and cosecant. What is the secant of beta? It's the cosecant of what? Say it. Yeah, 90 degrees minus beta. Similarly, what is the cosecant of beta equal to? The secant of what? Huh? Yes. That's called being a cofunction. We have sine, cosine, and tangent, and then they're cofunctions. So, what's so powerful about this? Well, we know the special angle values for 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, and so on. But we don't know them for 15. And we don't know them for 75. This allows us to discover new values that lie in between the unit circle values that we've discovered. So let's prove an identity using cofunctions. Given A and B are complementary angles, verify cosine squared alpha is equal to verify that cosine squared alpha is equal to 1 minus cosine squared beta. Given that A and B are complementary, prove this to be true. What did it mean for A and B to be complementary?
Equal 90 degrees.
They what?
They equal 90 degrees.
So alpha equals 90 and beta equals 90?
No, they both add up 90 degrees.
Aha! This gives us that they both add up to 90 degrees. Big difference of them both being 90 degrees. Okay, so that equation is just begging me to solve for one of the variables. Let's solve for alpha. Alpha is 90 degrees minus beta. So cosine squared alpha, we're going to start with this, and we're going to work towards this 1 minus cosine squared beta. So cosine squared alpha is the same thing as cosine squared 90 degrees minus beta, is it not? But let's come over here and look at what cosine of 90 degrees minus beta is. What is it? Cosine of 90 degrees minus beta is equal to what? There we go. So when you square it, it equals sine squared beta. What now? I want to show that this, what we're starting off with, ends up equaling this. This is what I want to show. How do I show it? What? Utilize the Pythagorean identity for this trigonometric functions in terms of beta? Why? That's a wonderful idea. Sine squared beta plus cosine squared beta should equal 1, right? This is the what identity? The what Ian identity? What identity is that? The Pythagorean identity, right? Sine squared beta is right here. But I want to solve for it alone. So I'm going to take this cosine squared beta to the other side. So I get sine squared beta is equal to 1 minus cosine squared beta. Right? It's the same thing, right? So let's replace it. Now what? Huh?
You're done.
Oh, you're done?
Yeah, done.
You sure? Okay, I overused it today. It's not working as well. Yeah, you're done. You put a box, and inside the box you could write QED, which stands for Quod Erat Demonstratum, which is Latin for thus it has been proven. It does not stand for quantum electrodynamics, unfortunately. We can talk about some quantum electrodynamics here in this class in a little bit. Does that make sense? All right. Okay, class is over.